active galaxies. So we talked about normal galaxies, and really this should be maybe a better way of putting this is called a section called active galactic nuclei. So nearly every big galaxy at one time in its life was an active galaxy, which means its nucleus was active, and I'll explain what that means. But one reason why I call it active galaxies is because the growth of the active, or the whatever's making the active galactic nuclei work, actually, and what it does, it feeds back into the growth of the galaxy. So if we look at this picture, this is a picture of the sky, the same part of sky, in visible light on the left, and in X-rays on the right. And if you look at visible light, and the angular resolution is much better in the visible light than the X-rays, but if I look in the visible light, I see lots of fuzzy things, right? And it's not because the angular resolution is poorer on that side, it's actually better. On the other side, I see lots of little dots, little points, right? And what those are, if we match them up, let's see if we can match one up. Maybe this guy matches up with that guy. And this guy, I don't know what those match up with. Maybe there isn't anything over there. So oftentimes, these little dots will match up with a galaxy over here. And if we think about very precisely where it matches up right with the center of the galaxy, right? So in the X-rays, the galaxies, it's their nuclei that are bright. And we have to understand why their nuclei are bright. And in fact, if I were to look at the picture, not every galaxy on the left has a dot on the right. So not every galaxy has an active nucleus. Our galaxy right now doesn't, but this is looking in distant space. Like for example, over here, here's a good sized galaxy, right? And there's no real bright thing right there. Here's another good sized galaxy. I'm pretty sure there's nothing that extraordinary in this region. This guy, in fact, if you look at it in the optical, you can see that there's a little bright thing in its middle as well. Right? So a large fraction, maybe about 10% of galaxies have these nuclei. And they really show up when we don't look at visible light, when we look at other wavebands. So something like those guys are pretty dramatic. If we look at somewhat less dramatic examples, we find somewhere between 20% and a quarter of galaxies don't really fit well in the Hubble scheme. They're much too bright. And the radiation, this extra radiation, is non-stellar, which just means it doesn't come from stars. So it's almost like saying it's extra. That makes sense. And it's invariably, it comes from activity near the center of the galaxy. And we talk about three different types, maybe for historical reasons: Seyfert galaxies, radial galaxies, and quasars, right? And the Seyfert galaxies, they're just named after this guy, Carl Seyfert, and he was looking at spiral galaxies, and he found a bunch of spiral galaxies whose central regions were much brighter, meaning thousands of times brighter than you would expect for a normal spiral galaxy. Now, if you look at this guy, the nucleus isn't brighter than the entire galaxy, right? You still see the galaxy, just if you look in the middle, it's much brighter than you would expect. And that's basically what is the Seyfert galaxy. So if you look at one of these guys, so this is in the X-rays, this is how many X-rays per second we get from that core. This is a different Seyfert galaxy, not Circinus. But you can see what happens is is the X-rays can go up and down by a factor of 4 over the course of, so if you think about these units, from here to here is 100,000 seconds, right? So this is 50,000 seconds. So if you look at this, it's shooting up and coming back down in about 10,000 seconds. That spike. 10,000 seconds is about 3 hours. Right? So what that tells us is, is that this object that's dominating the light is only 3 light hours in size. Right? Because there's no way it could turn on and off that fast if it were much bigger than that. Right? And why is that? So let's imagine if I had a bunch of stars, an object or a bunch of stars that's 10 light years across, right? Just for argument's sake. And somehow I get to turn all of those stars on and off all at once. Let's say I turn them all off in an instant, because I can. What I would see from Earth is I would first see the front of that group of stars turning off, and then 10 years later I would see the back, because it takes 10 years for the radiation from the back to reach the Earth relative to the front. So if I were to turn them all on at once, all off and on at once, from Earth's point of view, I would see it going off, and that would take 10 years, and then it would go on again, and that would take another 10 years. So if I go back to my Seyfert galaxy, it went on and then off in 3 hours, which tells me that that region, whatever it's emitting, is really less than 3 light hours across. And if we use that analogy of that bunch of stars, it's probably less than 1.5 light hours across, right, from one side to the other. So it's really, really, really small, yet it can emit as much radiation as an entire galaxy. Right? So this is why we have where the puzzle lies, right? So it's a really small region, the size of the solar system, yet it can create as much energy in X-rays, gamma rays, radio waves, and even visible light as the entire galaxy of stars does. So this is another example of an active galactic nucleus, and it's maybe a bit more dramatic. This is a radio galaxy, and these are named just for historical reasons. So this guy was the brightest radio source in the constellation of Centaurus, so Cen A for like the brightest. And what you see here is basically an elliptical galaxy, except the elliptical galaxy has dust, which we see here in the middle, and it has these pesky jets flying out of emission, right? And we saw one of these already. That was in that galaxy M87. I showed you that elliptical galaxy. That elliptical galaxy is also a radio galaxy. So these are bright in the radio. And again, in this case, the amount of energy coming out is similar to the galaxy as a whole, but doesn't outshine the whole galaxy. You can still see that there's a galaxy there. So the basic idea that one's forced to come to is the only way to produce that much energy in such a small volume is with a black hole. So these active galactic nuclei are thought to be supermassive black holes. So the black hole that fuels M87 that we saw its jet coming out probably has a mass of around 2 billion solar masses. So 1,000 times the mass of the black hole in the center of our galaxy. And depending on how you look at the galaxy, from which direction you're looking, you'll see different things, right? So if the different components that we've seen so far is a bright region with lots of light coming out, we also see these jets of radiation, but we think those jets are particles being launched from the black hole at nearly the speed of light. So depending on how we look at on this supermassive black hole that's accreting, we'll see different things. So if we are looking from the side over here, we'll see a picture like this guy. We see two jets coming out. We see both jets, right? We see the one on the top and the one on the bottom. But we can't really look right into the center of the galaxy, this central region near the black hole, because it's blocked by the gas that the black hole is accreting, which is here written as Taurus, right? So what we see are the jets, and maybe we see some clouds over here that are excited by the X-rays down here. So we'll see emission lines from these clouds, and that's called the narrow line region, right? So the X-rays in here that are generated, we don't see them directly, but we see them excite the gas up here, okay? Now, if we start looking down this way, we can actually see into where the black hole is. So we can see the X-rays coming from the middle. We can also see gas that's moving very fast around the black hole down here, which is called this broad line region. And we see lots and lots more radio waves from this guy. That's what it means called radio loud quasar. As you move up and you're looking right into the central region, you get to see all the light that's coming out near the black hole. And what will happen is that light can dominate the light of the entire galaxy. And when the light is dominating the entire galaxy, we call that a quasar, right? Quasi-stellar radio source. And then you have this other funny thing. So for example, in the galaxy M87, we saw a jet coming out one end way, right? You didn't see a jet on the other side, if you remember the picture. And why would that be? It's not because the galaxy only has one jet. It actually has two. The one jet that we see is coming at us at nearly the speed of light. So its radiation is blue shifted and made brighter, the one that's coming towards us. The one that's going away from us, just by analogy, is going away from us at nearly the speed of light. So that jet on the other side, it's there, but its radiation is redshifted and diminished. So you don't actually see it. You can have a ratio of maybe a factor of 1,000 between the one that's coming towards us and the one that's going away from us. So when we're looking at it from this point of view, this jet over here, even if we could see it, it's not going to be very bright just because it's going away from us at nearly the speed of light. And the one that's towards us looks very bright. Okay? If we actually happen to be looking straight down the jet, we see something called a blazar, which means that the radiation is so much dominated by the black hole that we see no evidence of there being stars in the galaxy at all, believe it or not, in the case of those. So let's just look at one of the first quasars to be discovered, and this is why people got so upset, or whatever, excited, is a quasar that was discovered in the radio called 3C273. And 3C273 is in the ecliptic. So what it meant is that they measured it, I believe, the moon going in front of it. So they could measure when it winked out due to the moon going in front of it, so they knew exactly where it was in the sky. So then they went to it with an optical telescope, and this was the first one that they did it. They looked at it and said, oh, that looks like a star. In fact, it looks like a 13th magnitude star. You can see this guy with an amateur telescope. So they said, it looks like a star. It's a radio source, so they call it quasi-stellar radio source, quasar. Then they went and they say, well, the next thing to do is take a spectrum of this apparently ordinary-looking star. And here's the spectrum they got up here. So it has hydrogen beta, which is just a normal hydrogen atom going from the 4th level down to the 2nd, and then 5th to the 2nd, 6th to the 2nd. And you can look in a spectrum of hydrogen, let's say, or a star that's not moving away from us, and the lines are here, here, and here, and they got shifted over by a huge amount, right? So this redshift of this guy was, I don't know, well, we can't really see the numbers. So there it says 15, 16, and I don't know why those particular numbers are written there, but I guess it moved from here to there, right? So this is 5,000 angstroms, and this is 4,000. So this guy got moved from maybe 4,500 angstroms up to 5,000 angstroms. So its redshift is like 0.1. But it's a 13th magnitude star at a redshift of 0.1. So they realized that this object, whatever it is, it's really far away and it's still really, really bright. So it must be producing a huge amount of energy. So this led to the puzzle of these quasars. So they had these really funny lines. They were just hydrogen lines that had been redshift extremely. And now we know about 30,000 quasars that are from relatively close to us, 240 megaparsecs, out to 9,000 megaparsecs, meaning, when the galaxy was much, much younger. So we have quasars that we see at a redshift of 6 or 8 when the universe was much, much younger. So these objects, these big black holes accreting, they got started in the very early universe and they continue till now. I don't know whether this picture is worth looking at without the lights. I don't think so. So we can look, this is our friend M87. So we left off talking about active galactic nuclei, and a great example of one is in a big elliptical galaxy in the center of the Virgo cluster, which is called M87. Now, this picture kind of shows something how AGN, or how the light from an active galactic nucleus is different. If we look at the top picture, that is in more or less visible light, or it's how your eye would see it, right? So the blue color of the jet is because the jet is blue, right, from our point of view. And the stars are peaked around the yellow. Now, however, if you look in these other bands, in the radio, in the X-rays, and in visible light, the jet itself and the active galactic nucleus here in the center, are all bright, in all of these energies of the light, whereas the stars aren't, right? The stars are gone from those pictures. So if you kind of summarize that, the radiation from an active galaxy occurs at all energies, from X-rays to radio, even in the gamma rays, which doesn't show here, especially those guys where the jet is pointing at us, the blazars. Whereas in normal galaxy, the radiation peaks in the visible, which is no coincidence because we live near a star, and the star's light peaks right where our eyes are most sensitive. And in normal galaxy, the light is dominated by the stars. So what happens is you have two components to the radiation from an active galaxy, and if we look down at the bottom, that gives you an idea of what they are. The first is radiation from stars, which are essentially
hot objects that are glowing because they're hot, and we call that thermal radiation, and that has that spectrum which we call a black body spectrum, more or less. There'll be spectral lines in that. But on top of that, the jet from the AGN, which we can see here, what's radiating there are electrons who are moving very close to the speed of light, and they're moving in a magnetic field. So that's why we call this synchrotron radiation. So a synchrotron is a particle accelerator, first with electrons, where the electrons go around in a circle nearly at the speed of light in a magnetic field. And what they do is, because they're being accelerated in the magnetic field, they emit radiation. And that radiation, we call it synchrotron radiation. But the key thing about it is that radiation occurs at a wide range of energies. So when those electrons are being accelerated by the black hole and ejected in this jet, they're emitting radiation all the way from the radio to X-rays and gamma rays. So active galaxies have this second very important component, synchrotron radiation, which is continuous. There's no lines in it, and at a very, very wide, very broad band. And when we look at objects like these blazars, this component of synchrotron radiation is completely dominant, and we can't even see the thermal radiation. So they're very hard to figure out because you don't see any spectral lines. So if we think about what is this central engine of the AGN, we had these components that it can turn on and off in the matter of hours. It has to emit a huge amount of energy from that small volume. And the only way to really make this work is with a black hole. Because when material flows into a black hole, you can release something like about 10% of its mass energy, 10% of mc squared, can get released as it flows into the black hole, or perhaps even a little bit more. Whereas if you remember, a star, it's not 10%, it's a little less than 1%. It's the entire evolution of a star, right? If you remember, when we converted 1 kilogram of hydrogen into helium, we lost 7 grams of mass. So little bit, 7 parts per thousand. This has to be 10% or higher efficiency, okay? So furthermore, we can think about if it's putting out so much energy, its mass has to be really, really large to keep the whole thing from flying apart due to all of the radiation coming out. And that pushes us to conclude that the object in the middle has to be very massive. So it's very massive, very small, and when you combine that, the only possibility is a black hole. Now, this is a picture of perhaps is what's going on in the very middle, that we have material flowing towards the black hole in an accretion disk, and depending on how much accretion is going on, the disk may be thicker, like on the right, or thinner on the left, and as it flows into the black hole, some small fraction of that material gets ejected vertically, and you can see if the accretion disk is thicker, it'll be that's called a sort of an accretion funnel here. This jet will be narrower, whereas if the accretion disk is thinner, it can be broader. It just has to get out of that region. Now, if we think about the different components of the radiation that we're getting, as the material flows down through this accretion disk, it gets hot and it glows. For a supermassive black hole like this one, that glowing is in the far ultraviolet, and the X-rays that we see are from this jet. If we bring the black hole down to a mass of a stellar mass black hole, like the ones we see in our galaxy, the radiation from the disk and the jet are both X-ray radiation. Okay? So as you go to more massive, the accretion disks get a bit cooler, but still we see X-ray radiation and gamma rays from the jet in both cases. So if we imagine a black hole being 1 billion solar masses, its radius is about 1 billion times 3 kilometers, 3 billion kilometers, so about 20 AU, which is sort of like, that's pretty big. It's quite a bit bigger than the orbit of Saturn, but it's in the realm of what a solar system looks like. So this central black hole is sort of the size of our solar system, and it's responsible for all of the energy coming out. So a billion solar mass black hole is like the black hole in M87. So how do we know that we're right, that we have this material flowing around the black hole? For a nearby black hole, we can measure the gas right in the vicinity of that central mass. And what we see, in fact, is that the gas is blue shifted on one side and red shifted on the other side. And then by that motion, we can just use Kepler's law to estimate the mass of what's in the middle, which we sort of argued from circumstantial ways has to be billions of solar masses. So here it is with the gas. In the center of M87, we can look at the motion of the stars around that black hole, and they move a lot faster as they get closer to the black hole. And we can then infer the mass of that black hole, and we get numbers. Remember, in our galaxy, we saw individual stars moving around. We got 2 million solar masses. These guys have about 1 billion solar masses. So if we think about what these black holes have been doing since the beginning, we see a funny coincidence, or I don't know why it kind of goes really down like that, but if you look at when we can measure when the number of quasars are around, we sort of count the mass of quasars or their growth with time. So M sun per year is how the quasars are growing, divided by a volume, millions of light years, and then they have to multiply it by 10 to the minus 3 because they're to just get it on that scale. You can see that the age of the quasars, when there were lots and lots of them, was a few billion years after the Big Bang. So on the right, on the left is the beginning of time, and then we go out today to now. So there were lots more quasar activity early on than there is now, okay? And it kind of peaked a few billion years after the Big Bang. On the right is how stars are being born over cosmic time. For example, our sun was born around here, right? Just because now we're at 13.8, our sun is 4.5 billion years old, so about 9 billion years after the Big Bang is when the sun and the earth and all that formed. Our sun formed relatively late in the game. If we look back in time, you can see that the stars, when there were lots of stars forming, was the same time as there were lots of AGN, right? Now, how are those two connected, right? But they're definitely correlated, that star formation and AGN are together. Maybe when you have lots of star formation, you feed the black holes more, so you get lots of AGN activity, or maybe if you feed black holes, it makes lots of stars form. But we can see this correlation. This is black holes and forming of stars through time, But we can also look at different galaxies, and we see a sort of interesting correlation there that's actually very tight. So if we look at a galaxy, whether it's an elliptical galaxy up on the top left, top right, or a spiral galaxy with a bulge, which is given by the yellow stars, what we find is as the mass of that bulge goes up, and in the case of an elliptical galaxy, the entire galaxy is a bulge, so does the mass of the black hole in the middle. And one thing to keep in mind, this ratio is something like the black hole's mass is maybe a couple thousandths of the mass of the bulge. So, like whether it's the black hole making the bulge bigger, or when the bulge grows, it causes the black hole to grow, we don't really know just yet. But one thing that you could imagine is if I build up bigger groups of stars, if I were to take two little guys down at the bottom and merge them together and get something bigger like this, the bulge would grow and the black hole would grow too in proportionality, right? So here it shows it in a more mathy way. And you can see that, I mean, it's not the greatest correlation. There's some scatter. But starting way down at the bottom, we have our galaxy, in fact, who has a kind of small black hole mass and not a big bulge. This is the Milky Way. And as we go up to bigger and bigger galaxies, so does the black hole mass get larger and larger and larger. So that's it's one of the sort of tighter correlations. So we see now among galaxies, we see as they get more luminous, their velocity of the stars increases, but also we see that the mass of the black hole in the middle increases as the galaxy increases. And we don't understand it. So, you know, you can ask me why, and I'd say, I don't know. I could make up some reasons. So this is an area of active research. Is there anything else to say about that? So, so if you imagine taking two galaxies and merging them together, which happens a lot, their black holes will also ultimately orbit each other and merge together. So as you grow, if you grow galaxies by merging them together, so too do the black holes end up merging together. Now this merging black hole, so here we have colliding galaxies, and if we look in the middle, we see sort of two AGN in the middle, right there. So that's a pretty amazing thing. These guys will gradually spiral closer and closer to each other and merge eventually. And that final merger we'll see in gravitational radiation, just like we've seen small black holes merging together and neutron stars in gravitational radiation, except the frequency of this is much, much lower. It's like not thousands of oscillations per second at the end, but of order one oscillation per second or even less. Like imagine if it's supermassive black holes and it's this 20 AU thing, that means it takes light about 3 hours to go around, or a couple hours. So that's the final frequency of these two black holes orbiting each other. So that's something that might be observed in the future with another experiment like LIGO, but in space, called LISA.